Okay. Ladies and gentlemen, we are busy with Chapter 8, Internal Forced Convection. We've done all the paragraphs from 8.1 to 8.6. But there are just two more problems that I want to do with you, just to make things more clear to you. And the first problem is problem 8.38. And the problem says air at 10 degrees Celsius enters a 12 centimeter diameter and a 5 meter long pipe at a rate of 0.065 kilograms per second. The inner surface of the pipe has a roughness of 0.22 millimeters and the pipe is nearly isothermal at 50 degrees Celsius. Determine the rate of heat transfer to air using the Reynolds number relations given in equations 866 and equations 871. Okay, so of the about 10 equations that were given for turbulent flow, it specifically specifies the two equations that should be used for this problem. Okay, so the problem, in summary again, there's our tube. Okay, it's air at the temperature of 10 degrees Celsius and a mass flow rate of 0.065 kilograms per second. The tube diameter is 120 millimeters. And the tube length is 5 meters. The surface temperature is maintained constant at the temperature of 50 degrees Celsius. The surface roughness, epsilon, is equal to 0.22 millimeters. Let me just repeat the problem again. Air at 10 degrees Celsius enters a 12 centimeter diameter and a 5 meter long pipe at a rate of 0.065 kilograms per second. The inner surface of the pipe has a roughness of 0.22 millimeters and the pipe is nearly isothermal at 50 degrees Celsius. Determine the rate of heat transfer to air using the Reynolds number relations given in equations 866 and equation 871. So we have to determine the heat transfer rate according to equations 866 and according to equations 871. Okay, so if we have air flowing through this pipe and the pipe temperature is 50 degrees Celsius, then firstly we know that the air temperature cannot be more than 50 degrees Celsius if it goes out. Okay. At most it can be 50, but not more than 50. So you can make your guess in terms of what do you think that outlet temperature should be. What I've done is I've assumed a bulk temperature of 20 degrees Celsius. Okay. So just 10 degrees Celsius higher than the inlet temperature. Bulk temperature 20 degrees Celsius. And at 20 degrees Celsius, in the tables we can get the properties. Density is equal to 1.204 kilograms per cubic meters. The thermal conductivity K is equal to 0.02514 watts per meter degree Celsius. The kinematic viscosity is equal to 1.516 e to the minus 5, 10 to the minus 5 meters squared per second. And Cp is equal to 1007 joules per kilogram Celsius, and the Prandtl number is equal to 0.7309. Let me just repeat the values for you. At the bulk temperature of 20 degrees Celsius, the density is equal. The density of the air would be equal to 1.204. Thermal conductivity K is equal to 0.02514. The kinematic viscosity is equal to 1.516 multiplied by 10 to the minus 5. CP 1007, and the Prandtl number 0.7309. Okay, you all understand the problem? Any questions? Nothing? Okay. Let's start by calculating the average velocity, because the mass flow rate is given. So the mass flow rate is equal to rho multiplied by the cross-sectional area multiplied by the velocity, or let's call it the average velocity. The mass flow rate is given as 0.065 equal to the density, which is equal to 1.204 multiplied by the cross-sectional area through which the flow occurs, pi divided by 4 multiplied by 0.120 square multiplied by the average velocity, and you can go and solve the average velocity as 4.773 meters per second. Okay, let's calculate the Reynolds number, because we want to know if the flow is laminar or turbulent. The Reynolds number is equal to the average velocity multiplied by the diameter divided by the kinematic viscosity. The average velocity is equal to 4.773 multiplied by the diameter, which is equal to 0.120, divided by the kinematic viscosity, which is equal to 1.516 multiplied by 10 to the minus 5, and that gives us a Reynolds number of 37,785. Okay. So we have turbulent flow. Turbulent flow because for a tube, the flow changes from laminar to turbulent flow at about 2,300. We've got a section through which we've got transition flow up to maybe 10,000 or 30,000, but it is definitely more than that. So we've got turbulent flow. Let's look at the developing lengths. The developing lengths would be equal to 10 diameters, which would be equal to 1.2 meters. Okay, 1.2 meters. So in terms of this tube, which has a length of 5 meters, it would take about 1.2 meters before the flow is fully developed. So we will have something like that up to that point, and from there on it would be constant. Okay, so we can see that about for 80% of the tube, the flow would definitely be fully developed. And therefore we assume, that the flow is fully developed. And if it is fully developed, we need to get the Nusselt number. With the Nusselt number, with one of them, or actually with both of them, we need the friction factor. But in this case, the wall surface has been given. So epsilon divided by d is equal to 0.22 millimeters, the surface roughness. So because this is in millimeters, we have to use this value, the diameter also in millimeters. Obviously, you can use that in meters and that in meters, but both of them would give us epsilon divided by d as equal to 0.0001833. Okay. So many of the equations you'll see in the literature are for smooth tubes, and not many are for rough tubes. Okay. Now, fortunately, and this is something that I've found through lots of experience, is that all the tubes that we buy these days are actually smooth tubes for all practical purposes. It's very, very difficult to get a rough tube. In the old days, the tubes were casted, and then they were rough. But these days, 99% or even more of all the tubes which are available are actually smooth tubes. And therefore, then you can use the smooth tube equations. So on the Moody chart, if you look at the friction factor divided by the Reynolds number, if the flow is laminar, then the friction factor is equal to 64 divided by the Reynolds number up to the transition point, and then this line is the line where epsilon divided by d is equal to 0. Okay, and that is the smooth tube line. And with the previous lecture, I've given you equations that describes this line. Okay, but now we cannot use that line because we've got a rough tube. So epsilon divided by d is equal to 0.0001833, and we have two possibilities. The first one is you can go and look at your Moody chart, and your Moody chart is also in the appendix of your textbook. It is a figure 820. And figure 820 at the back of your textbook, there is a Moody chart. So you can go and look at the Reynolds number of 37,785, and from there you can get the friction factor. Okay. However, you will see that these lines are very, very close to each other, and the Reynolds number scale here is a log scale. So it is very difficult to read. You can get the order of magnitudes, but to get a very accurate value is very difficult. So an equation which gives us the friction factor for all these other equations is the Colebrook equation. Colebrook equation, I don't know if you've done it in fluid mechanics. It's just an empirical equation, and it is also in figure 820. If you read at the bottom of the figure, you'll get the equation there, and it is in your textbook also. And the Colebrook equation gives us 1 divided by the friction factor is equal to minus 2 times the log of epsilon divided by d divided by 3.7 plus 2.51 divided by the Reynolds number multiplied by the friction factor. Okay. So what you will see is that we cannot solve the friction factor explicitly. So what I did is I said, let's choose the friction factor as equal to 0.001. I've put it in there. You calculate the friction factor and you put it back into the friction factor and you iterate it. And it was within 3 iterations before the friction factor converged to 0.2667 very, very quickly. Friction factor 0.2667. Okay. Okay, now equation 866 is one of the correlations which gives us the Nusselt number, and the Nusselt number is equal to 0.125 multiplied by the friction factor multiplied by the Reynolds number multiplied by Prandtl to the third. Very, very simple equation. 0.125 multiplied by the friction factor, which we have just now calculated, 0.2667, multiplied by the Reynolds number, which is 37,785, multiplied by the Prandtl number. The Prandtl number is there on the first board, is equal to 0.7309 to the third, and that gives us the Nusselt number of 114.7. Okay, Nusselt number of 114.7. The Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity. We've just now calculated the Nusselt number, which is 114.7. That is equal to the heat transfer coefficient, which we want to determine. The diameter we have is 120 millimeters, divided by the thermal conductivity, which is equal to 0.02514, and that gives us the heat transfer coefficient as 24.02 watts per meter degree Celsius. Okay. Now, one of the paragraphs that I've spent 2 lectures on because it is so important, okay, was the 2 cases where, firstly, we have a constant heat flux, and the case where we had a constant surface temperature. A constant heat flux and a constant surface temperature. For the constant heat flux, the mean temperature on the inside of the tube is a straight line. Okay, so that is the mean temperature. And then the surface temperature, oops, we do something like this. It's parallel towards that line. Okay. After it has been fully developed. Okay, so that is the surface temperature, and that is a function of x. Okay. For the constant surface temperature case, the surface temperature is a constant, and then we've shown that the temperature distribution does something like that. Okay. The mean temperature is a function of the NTUs, e to the number of NTUs. Okay. So let's calculate the NTUs. The NTUs is equal to the heat transfer coefficient multiplied by the area divided by the mass flow rate multiplied by the CP. The heat transfer coefficient is equal to 24.02. The surface area is equal to pi multiplied by the diameter multiplied by the length divided by the mass flow rate is equal to 0.065 divided by 1007. And that gives us the NTUs of 0.6917. Okay. 0.6917. What does it mean? It means that this temperature is not even going to get close to that surface temperature. If it is about 5, then the temperatures would be very close. So the outlet temperature is equal to the surface temperature minus Ts minus Ti e to the minus NTUs. Okay. So this equation describes that line. for the case of a constant surface temperature. Okay. The surface temperature is equal to 50 minus, again the surface temperature 50, the inlet temperature is equal to 10 degrees, E to the minus NTUs 0.6917, and that gives us an outlet temperature of 3 degrees Celsius. Okay. And we can see it is not even close to the 50 degrees Celsius wall. Right, so at this stage we are supposed to say recalculate the bulk temperature. Okay. We should recalculate the bulk temperature at this stage. So the good bulk temperature would now be 10 plus 30 divided by 2, and that would be 20 degrees Celsius, which is actually the bulk temperature that I've chosen. So if you've chosen a higher one, then you just need to recalculate, and if it wasn't 20 degrees Celsius, you need to go through all the calculations again. You don't have to do that in the test and exam, but you have to tell me. You have to recalculate TB and iterate. In this case, we do not have to iterate. Okay. Do not have to iterate in this case, but if you didn't choose the bulk temperature correctly, then you're supposed to do that. Right. So now we've got the outlet temperature and we can calculate the heat transfer rate. The heat transfer rate is equal to the mass flow rate multiplied by Cp multiplied by the outlet temperature minus the inlet temperature. The mass flow rate has been given as 0.065. Cp is equal to 1007 multiplied by the outlet temperature, which we have calculated now as 30, minus, the inlet temperature, which is 10. And that gives us a heat transfer rate of 1,307 watts. Okay. Now this is the first part of the problem. Remember, the question was determine the heat transfer rate using equation 866 and equation 871. Okay. So now we have to use equation 871, which is the equation of Gliński. Of Gliński. I'm not going to write out everything, but if you go and do the calculations, then you'll see the Reynolds number is equal to 105.2. The outlet temperature is equal to 28.8. So you are supposed to recalculate the bulk temperature like that. Okay. Recalculate again the outlet temperature, and the heat transfer rate would then be equal to 1,230 watts. So it's very, very close actually to that value there, within about 6%. Okay, something that hasn't been asked was the pressure drop. Let's just calculate the pressure drop also, just as an exercise. The pressure drop is equal to the friction factor multiplied by L of D multiplied by rho V squared divided by 2. The friction factor is equal to 0.2667 multiplied by the length of the tube, which is 5 meters, divided by the diameter, which is 120 millimeters, multiplied by the density, which is equal to 1.204, multiplied by the velocity squared, 4.773 square divided by 2, and that gives us a pressure drop of 152.4 pascals. Any questions, ladies and gentlemen? Before I clean everything. Okay, the next problem is going to be problem 8.50. And this problem says a concentric annulus tube has inner and outer diameters of 25 and 100 millimeters respectively. Liquid water flows at a mass flow rate of 0.05 kilograms per second through the annulus with the inlet and outlet mean temperatures of 20 and 80 degrees Celsius respectively. The inner tube wall is maintained with a constant surface temperature of 120 degrees Celsius while the outer tube surface is insulated. Determine the length of the concentric annulus tube. Right. So this is our concentric annulus tube. It means it's one tube inside another tube. Okay. But in this case, there's no flow through this tube. Or if there is, they didn't give us any information on it. Okay. The flow is through the annulus. Okay, so in the spacing between these two tubes, and the inlet temperature is equal to 10 degrees Celsius, and this surface is being kept constant at a temperature of 120 degrees Celsius. Okay. That would typically occur if in this inner tube we have condensation or boiling. The outlet temperature is 80 degrees Celsius. This diameter, the inner tube diameter, is 25, and the outer diameter is 100 millimeters. 25 millimeters and 100 millimeters. And it is water flowing through it, and the mass flow rate of the water is equal to 0.05 kilograms per second. Okay, so water flowing through an annulus, inlet temperature 10 degrees Celsius, mass flow rate 0.05 kilograms per second, surface temperature is maintained at 120 degrees Celsius, this diameter is 25 millimeters, and that diameter is 100 millimeters, outlet temperature must be 80 degrees Celsius, and they ask us to determine the length of the tube. Okay, so the length of the tube is what must be determined. So just like with the previous problem, if we look at this temperature distributions that we can expect, T is a function of X, then the surface temperature is constant at 120 degrees Celsius. Okay. The inlet temperature is given as 20 degrees Celsius. So there's 20, and there is 80 degrees Celsius. So the flow occurs from this side, from the temperature of 20 to that side with a temperature of 80. And this equation, the mean temperature is equal to Ts plus Ts minus e to the minus n to U's Ti minus Ts. That is the equation for that line. Okay, in terms of properties, bulk temperature, a good bulk temperature would be the inlet temperature plus the outlet temperature divided by 2, which is equal to 50 degrees Celsius. And that is according to table 8.9, we can get all the properties. Okay, now something, ladies and gentlemen, that's very, very important is that some of you think that maybe it is better to go and calculate the temperature there and to use that as the bulk temperature for my properties. Okay, you shouldn't do that. The reason for that is that all the empirical equations that were derived were for the bulk temperature based on the inlet plus the outlet divided by 2. So the equations are based on this equation, the empirical equations. Okay. So at 50 degrees Celsius, the density is known as 988.1 kilograms per cubic meters. Cp is equal to 4181 joules per kilogram Kelvin. The thermal conductivity K is equal to 0.644 watts per meter Kelvin. The viscosity is equal to 0.547 e to the minus 3 kilograms per meter second, and the Reynolds number is equal to 3.55. We've got the mass flow rate, so we can, from the mass flow rate, get the velocity and then the Reynolds number, or from the mass flow rate, you can directly calculate the Reynolds number. Today, I've chosen to first calculate the velocity. The mass flow rate is equal to rho AV. The mass flow rate is equal to 0.05. It's equal to the density, which is equal to 988.1. The cross-sectional area is equal to pi divided by 4 multiplied by this part of the annulus, the flow through the annulus. So it is equal to 0.1 square minus 0.025 square. Okay. So this area is the cross-sectional area through the annulus, multiplied by the average velocity. From which we can calculate the average velocity as 0.00708 meters per second. So the velocity is quite small. The Reynolds number is equal to rho multiplied by the average velocity multiplied now by the what diameter? The hydraulic diameter, because the flow is through an annulus, divided by the viscosity the density is equal to 988.1. The average velocity we have just now solved is equal to 0.007, 08, multiplied by the hydraulic diameter, which is equal to 0.1 meters minus 0.025. 100 millimeters minus 25, so it is 75 millimeters hydraulic diameter. Divided by the viscosity, which is equal to 0.547 e to the minus 3, and that gives us a Reynolds number of 931, which means the flow is laminar. Laminar flow. Okay. We can go and calculate LH, how long it would take before the flow is fully developed, the velocity profile, which is equal to 0.05 multiplied by the Reynolds number multiplied by the diameter, or the hydraulic diameter. Okay, I'm not going to do the substitution, but it works out as 3.492 meters. And the thermal boundary layer would be equal to LH multiplied by the Prandtl number, and that works out as 12.39 meters. Okay. Now we have to make a decision. Okay. With this in mind, it takes 12 meters before the flow is fully developed, but they didn't tell us what the length of the tube is. That is what we have to determine. Okay. So let's assume that we have the situation where, if we look at the length of the tube, that we will have something like that. Okay. Where this is the 12.39 meters, and we hope therefore that the tube length is going to be much longer than that. If we do the calculations and we end up with a tube length of maybe 15 meters, then we know we took a shortcut, and we will have to look at the fact that the flow is developing. We need that Nusselt number. Okay. So we assume fully developed flow. Assume fully developed flow. And for a constant wall temperature, and furthermore, we have to remember the flow is laminar. Got laminar flow. Okay, now in table 8.4 in your textbook, table 8.4, as a function of the diameter ratio, which in this case would be equal to 25 divided by 100, which is equal to 0.25, there you can get that the Nusselt number is equal to 7.37. It's a very small table. Take note, I means the Nusselt number if the heating is on this wall here. So this is the Nusselt number on that wall. It might be that the heating is from that wall, from the outside. Then it would be the Nusselt number outside. So there are two values in the table. Okay. So you have to choose the inside one because the heating is on the inner wall. I've put it on ClickUp for you, some more correlations that we've just published for annulus flow. Just take note of it. You don't need to use that in the test or exams, but there are many of you that did come and see me who are busy with designs under the supervision of some of the other staff members, and I would recommend that you look at those equations. Okay, so now we've got the Nusselt number, therefore it's very easy to get the heat transfer coefficient. The Nusselt number is equal to the heat transfer coefficient multiplied by the hydraulic diameter divided by the thermal conductivity K. The Nusselt number is 7.37. is equal to the heat transfer coefficient multiplied by the diameter, hydraulic diameter, which is 0.1 minus 0.025, divided by the thermal conductivity, which is equal to 0.644. And from this, we can solve the heat transfer coefficient as 63.28 watts per square meter degree Celsius. Okay. Take note, sometimes the heat transfer coefficient is written as per degree Celsius and sometimes per Kelvin. It doesn't matter. Okay, so now we've got the heat transfer coefficient, and coming back to this equation, we can now use this equation to get the NTUs. And in the NTUs, we've got the area and the length. So TE is equal to TS minus TI e to the minus NTUs. Yeah, I've made a mistake here. TS minus TI. Should just be the other way around. TS minus TI. Yes. Okay, TS minus. Thank you. Okay, so this is the equation that gives us the temperature profile on the inside. The outlet temperature should be 80 degrees Celsius. The surface temperature was given as 120 minus 120 minus the initial temperature, which is 20, e to the minus NTUs. Okay. And this is equation 8.30. And if you use a red pen or something like that in your textbook, that equation, you should use your red pen on that equation. It's a very important one. It's one that is being used a lot. However, I would recommend that you do not write this as the heat transfer coefficient multiplied by the area divided by MCP, but rather as NTUs. Okay. The reason for that is the following. If we now calculate the NTUs, it tells us something. 0.9163. If that is the case, then we know that these two temperatures are not going to be close to each other. Okay. We are not wasting area. Okay, so the NTUs is equal to the heat transfer coefficient multiplied by the surface area divided by the mass flow rate divided by Cp. The NTUs has been given as 0.9163. It's equal to the heat transfer coefficient. The heat transfer coefficient 63.28 multiplied by the surface area. The surface area is pi multiplied by the diameter multiplied by the length divided by the mass flow rate, which is equal to 0.05 multiplied by Cp, which is 4181. And from here we can solve that the length is equal to 38.54 meters. Okay, so coming back to our assumption, we now know the length, it's 38 meters. So it means that about a third of the flow would be developing. So if you want to refine this problem, you have to take it into consideration, but it would be very difficult using the information that you have in your textbook. The reason is that there's no equation for the Reynolds number for developing flow in an annulus in your textbook. It is only the table which is available. And you will have to go and look at other literature to enrich the information that you're going to need.